Here are the solutions to test number 3 for ECE 46161 control systems. This test looks at digital control and controllers designed in the frequency domain. Now the first problem is convert from the S-plane to the Z-plane. Supposed to come up with the compensator K of S in the S-plane. What's the corresponding compensator in the Z-plane? To do that, I convert the poles to zeros as e to the st. So pole at minus 2 becomes 0.9048, minus 5, 0, minus 15. So the form of K of Z is the same as the form of K of S. 2 zeros, 2 poles in the S-plane, 2 zeros, 2 poles in the Z-plane. Each one maps as e to the st. To find K, match the gain at some frequency. Now typically we use DC, but at DC I get infinity, and saying that infinity equals K times infinity, solve for K doesn't really help. So pick some frequency other than 0. So here I picked J, radians per second. The gain of K of S at S equals J is 22.75. Pick K so that K of Z at the same frequency is also 22.75. Solving, I get 25.05. So here is K of Z. That's problem 1. Problem 2 is design a discrete time compensator so that this plant closed loop has no error per step input and a closed loop dominant pole at 0.8 plus j.2. So here what you're doing is I'm forming a closed loop system. Here G times K with unity feedback. When I do that, we're using root locus techniques. I want to place the closed loop pole at, let's try that again. So here's 0, here's plus 1, at 0.8 plus j.2. Now I start out with a pole at 0.95, 0.85, 0.6, and 2 zeros at the origin. To meet my specs, I need to add a pole at plus 1. That makes it a type 1 system, so there's no error per step input. I need to get rid of these poles. If I have 2 zeros, I have 2 poles. Add this last pole somewhere, slide it around so that the root locus passes through this point. With angles that up to 180 degrees. So that's the idea. To do that, I'll first pick the form of K of Z. I'll cancel 2 poles, add a pole at plus 1 to make it type 1, add a second pole somewhere. Pick this pole so that 0.8 plus 0.2 is on the root locus. Now to do that, I analyze everything that I know. I don't know K, I don't know A. Analyze everything else at my design point. Angle should be 180 degrees. It's not, it's less than that, so that's good. That means the pole that I ignored must add the remainder. It has 28.07 degrees. Doing some trig. I've got 0.8 plus 0.2. It's j.2. So this side is 0.2. Here's 0.8. Here's my pole at minus A. That's my angle. That's 28 degrees. So that says A is 0.8 minus this distance. And that's 0.2 over tangent of 28 degrees. Gives you A is 0.425. So here's the form of K of Z. To find K, any point in the root locus, G times K is minus 1. So here's G times K. At my design point, the gain should be 1, minus 1. So here's the 180 degrees. That tells me this pole is correct. The gain's wrong. Pick K to make the gain 1, and K is 5. So there's K of Z. Problem 3. Problem 3 is given the Bode plot, the blue line, find G of S. Well, to do that, I draw the straight line asymptotes at multiples of 20 dB per decade. So this is at plus 40, 0, minus 40. I've got a change of 40 dB per decade right here, so that says there's 2 poles at 0.6, another 2 poles at 31. To find the angle of the poles, I find the gain of the resonance. This is 18 dB, that's 4 dB. So the gain at the corner is 1 over 2 zeta. When it's 18 dB, then zeta is 0.06, 86 degrees. When it's plus 4 dB, or 1.58, 1 over 2 zeta is 1.58. Zeta is 0.313, or 71 degrees. So here's the form of g of s. To find k, match the gain at some point. So you can pick any point that you want. I chose 5 radians per second, but any point works. If I choose 5 radians per second, that is, at J5 radians per second, I should get 11 dB, or 3.548. Solve for k, and k is 321.3291. Problem 4. Problem 4 is the Nichols chart. Given this data, and this Nichols chart with the red line, what is that M circle? Find, when k is 1, what the gain margin is, what the phase margin is, and what k is. So the first step is to transfer the data to the Nichols chart. So I get 2 dB minus 130 degrees. So here's 2 dB minus 130, minus 1 dB minus 151 degrees, minus 1 dB minus 150 degrees, minus 4 dB minus 170, minus 4 dB minus 170, and so on. Then connect those points with the curve. That's the orange line. To get the gain margin. The gain margin is how much can I crank up the gain until I go unstable. That's this distance. That's about 7 dB. The phase margin is how far can I shift it left until I go unstable. That's this distance. That's 10, 20, 30, 36 degrees. K, fluorescence of M sub m, is I slide it up until I'm tangent. That's about plus 2 dB. And then to find out what M sub m is, pick any point. I could pick this one. That is 3.5 dB at 180 degrees. You could pick this point, pick that point, pick any point that you want. I chose this point right here, 1 at minus 162 degrees. Open loop, closed loop is g over 1 plus g, 3.196. This is a 3.196 M circle. That's problem 4. Problem 5 is design for phase margin. So given the system, find k of s so that there's no error per step input, a phase margin of 20 degrees, and a 0 dB gain frequency of 3 radians per second. So what that tells you is it's got to be a type 1 system, and at 3 radians per second, gain is 1 at minus 160 degrees. That's my 20 degree phase margin. So kind of one way to approach this, I start out in the S-plane, I pull at minus 1, minus 4, minus 10. Here's my design point, J3. I need to add a pole at s equals 0 to make it type 1. So k of s has to be in the form of something over s. If I do nothing, the phase is too much, so get rid of this pole. Still the phase is too much, so get rid of this pole. I now have 2 zeros. Add this pole somewhere. Slide it around till the angles add up to minus 160 degrees at J3. So that's the idea. So if this is the form of k of s, analyze what we know. I don't know k, I don't know a, analyze everything else. At J3, I should get 1 at minus 160 degrees. The angle's off, so the pole I ignored must add the remainder, 53.3 degrees. Doing some trig. This side is 3. This is 53.3 degrees. Find a. So that's just 3 over the tangent, 2.236. So here's the form of k of s. Here's g times k. To find k, at your design point, the gain should be 1. Pick k to make the gain 1, 2.34, and there's k of s. So this is one solution, and there's actually many solutions. I could cancel all 3 poles. That works. I actually don't have to cancel that second pole. This also works. As long as g times k at s equals J3 is 1 at minus 160 degrees, and it's type 1, that's a valid solution. So that is test number 3 for ECE 461.